Okay, we're going to continue our chapter 2 video here. Now we talk about energy balance. And what we have for energy balance is that total energy entering a system minus total energy leaving a system is equal to the change of energy of the system. So we can write that in terms of energy. So energy in minus energy out is equal to the change of energy of the system. We talked a little bit about this in the previous video. This is another way of looking at energy balance, or the first law of thermodynamics. And descriptively what that means is if we had, I'm going to go ahead and draw a arbitrary system, but just to say we have a box. And then inside the box, we're going to define the inside of the box as our control volume. So just basically we just dot the lining of the box and say whatever crosses this boundary is what we're interested in. So let's assume that this is a box and we have heat escaping out of the box. We're going to call that Q. We're going to say that's equal to 3 joules of heat. And now at the bottom here we might have a heat source, and we can have heat coming in. We could say that's equal to 15 kilojoules, or 15 kilojoules. So I meant to put kilo here, see if I can squeeze it in here. So it's 3 kilojoules escaping and 15 kilojoules entering at the bottom. Now it doesn't really matter what surface. They could all be happening on one wall. It's nice to spread it out so you don't get yourself confused. So it wouldn't matter if the heat is entering this direction or that direction, as long as it's entering the system. This is what we call the system here. We only care about what's crossing the boundary into it and what's crossing out of it. So out of it, into it. So then we say then that we also have work coming in. Let's just say the work, instead of drawing an arrow at this point, let me draw a shaft. And this shaft will have a propeller like that. Now it doesn't really matter where this shaft is connected. The only thing we know is that we are introducing work into the system that we call shaft work, or work SH. And we know that it's going into the system because we are applying it. We're bringing work from the outside into the system, and we're just going to say the shaft work that we're introducing is 6 kilojoules. And so now we defined, we have 3 components. We have 2 heat sources, or a heat source and a heat outage, and 1 work in. And that we can actually represent this work as basically another vector that comes in here like that. And we can just call that work in. And so now we have that the change of energy of the system is equal to basically this whatever's crossing the boundary. We know that there's 15 kilojoules coming into the system. So let me just go ahead and block off the put a parentheses around the heat related. So we know that's 15. So it's a positive 15 coming in, and there's a negative 3 coming out. So we go ahead and put a parentheses there, and then we have another source of energy coming in, and that's work. So we're going to basically call that, because if you remember from our discussion about sign convention, work going into the system is actually considered negative. And so from a previous discussion, the way we identify the first law is all the heat going exchanging from the system, either into the system or out of the system, we categorize that as Q, minus all the work, whether it's going in or out of the system, we categorize that as W, so it's minus that. is equal to the change of energy of the system. This is another way of writing it. And so this here is coming into the system, the work going into the system. We consider the system now lazy because we have to add work. And so the sign convention for that is actually negative. As far as the other arrow, so we have heat escapage. So for heat, it's opposite of the sign convention of work. So we'll just say when work is going into the system, we're adding work to it. So it's a positive amount of work that we're adding. And when heat is escaping, it's leaving the system, so it's negative. It's a little bit more intuitive dealing with heat and how the energy flows is positive when it goes in, negative when it escapes. Work is the opposite when it goes into the system, but we look at the system as it's lacking work, or we have to it's lazy and we have to add work into it. Positive work would be work coming out of the system. For example, an engine that produces shaft work, we consider that positive work. So that would be coming out of the system. But again, don't confuse the sign convention. So therefore, because work is negative, but yet we have this other negative sign here, this actually becomes a positive here. Actually, I should do a different color. So it's positive 6 kilojoules. And so we have that the total is now 15 minus 3 plus 6 is equal to 18 kilojoules. So we have that the net energy that the system experiences is a total of 18 kilojoules, and that's 15 minus 3. So that's 12 plus 6 gives us 18. And that's how we defined energy coming in and out of a system. All right, so again, don't get confused with the sign conventions. It's something that can easily confuse us. When we get into chapter 5, the way we define signs, whether it's a positive for work coming in, or negative for work coming in, positive for work coming out, that goes away because we start grouping everything that comes in on one side of the equation, everything that leaves the system on the other side. It kind of helps us to keep track of everything. So for now, just kind of hang tight. And let's see what else we can discuss. I want to talk a little bit about efficiency. So let's go ahead and start a new page. So I need to go ahead and darken the screen. So efficiency is the topic now. So we talk in terms of how efficient something is. And there's many definitions to it. For energy related definitions, we can just say it's energy utilized, so that's actually energy that is used versus energy supplied. So that's an example of efficiency. So let's look, for example, let's look at a case here where we have a pot of water. Let's go ahead and do that. So let's just say you're heating up some water inside of a pot. And I suppose I can go ahead and just say, all right, well, let's go ahead and there's water in here. Well, that's very bright water. Maybe we can darken the water a little bit. All right. And let's suppose that we have this on top of a burner, or basically we have it sitting on top of an electric warmer type of device that has standoffs here. And that device is basically plugged into the wall. So this is an electric powered warmer or heater, you can say. Let's suppose that there's 5 total. Let's see if we can go ahead and do this. 5 kilowatts of energy that is coming from this heating plate. Okay, so that's 5 kilowatts of energy rate. Let's assume that of that 5, 3 of it is used to heat up the water, and then there's 2 basically escapes to the surroundings. So the way we would go ahead and identify, oh, and by the way, we give energy typically a symbol eta. All right. So eta is the symbol we use for efficiency. So if we were to go ahead and calculate the efficiency, we would say, well, what's the energy? You can do it any way you want. At the bottom you say energy supplied. Well, we know that the energy supplied is this 5 kilowatts. And the energy utilized, well, what's utilized? What's the point of this, of what we're trying to do? We're trying to heat up water, right? So the energy that's going into the water, and here, I mean, we really should draw a control surface. So we should kind of draw control volume. It's basically the inside of the water. The boundary of the water is where we would define our control surface and our control volume. And so we're looking at what's crossing that, right? We have the 5 kilowatts that's going in. We know 3 kilowatts is staying and 2 kilowatts is leaving. So we know that what's utilized is basically those 3 kilowatts to heat up the water. The 2 kilowatts is wasted. So therefore we just say 3 kilowatts. And that gives us an efficiency of 0.60, which is 60%. So this, based on this scenario here, we are seeing 60% efficiency of heating up the water. And that's how we pretty much deal with efficiencies. There's other ways of dealing. Going to hit start a new page. In more practical terms, we are talking about mechanical systems, and so that was a situation we're just looking at heat being transferred to warm up or to heat up water. So in general, we're talking about mechanical systems. So if we say for mechanical efficiency, we say that the this is equal to, we have the symbol eta, and we typically just write mech for mechanical efficiency, and that is the it's basically the energy input. So it's the mechanical energy input at the bottom, and at the top we put the mechanical energy output. And what that is, so in symbolically, we'll just say that's E. We're going to say E mech out. And over E mech in. And so for efficiency, the input is always larger than the output because of inefficiencies or heat loss or friction or anything like that. You're always going to put, you're always going to get out less than what you put in. So this is a mechanical efficiency, and that would be, so it's, you could technically, it could get to 100% efficient, but typically you're less than 100%. And if we were going to say, for example, the efficiency of a pump, we would say that the efficiency of a pump is how do we characterize a pump? Well, we're adding energy to a fluid, so I'm just going to say it's the mechanical energy increase in the fluid divided by, so that's what did I do? Okay, divided by the mechanical energy, and that is input. Let me go ahead and zoom out of here. All right. And typically, that is basically the change of energy of the fluid. And we typically use rates, kind of like in kilowatts. And so that's the change of energy of the mechanical energy of the fluid divided by what's running the pump. It's usually it's a shaft. Usually a motor is basically turning the wheels, the compressor. I'm sorry, so it's usually like a propeller or a rotary blade, something that's given us increased mechanical fluid energy. So that would be kind of how you would characterize that. And again, work shaft. So the amount of energy you transfer to the fluid is always going to be less than 1. Ideally, it would be 1, so it would be 100%. What you put in is what you get out. But because of mechanical losses, and then what's the change of energy of the mechanical fluid? Well, that's basically the change of state of the fluid, or you look at the energy that comes out of the pump minus the energy that the fluid has when it comes in. So it's your change of energy of the mechanical of the fluid, the change of rate of energy. It's how much energy that the fluid's experiencing. Well, the only way to know that is if you know relative to when the fluid comes in, it's at a lower, for example, pressure. When it exits, it's at a higher pressure. And so that's associated with an increase in energy rate. If you suction the pump, if you did some kind of or if you diffused it, where in other words you drop the pressure as it comes out, then maybe this becomes negative, right? Maybe the energy that comes in to the pump is larger than what comes out. That's fine. You can do that. All right. And then we deal the same thing with turbines and other components. You're going to see we can have for a turbine, for example, it's usually the opposite of a pump. So in a turbine, we're actually, like I said, we have a high energy fluid content coming into the turbine, and then we're trying to recoup mechanical energy out of the turbine. So we're trying to convert, for example, high energy steam into mechanical rotary shaft that we can then connect to a generator to turn on the lights. So in that case, for a turbine, we would say the efficiency would be, what would be coming out? Well, probably be easier to illustrate what a turbine looks like, but basically you're trying to convert fluid flow energy into shaft energy. So what comes out is work of the shaft out, and then what's at the denominator is basically the change of the energy of the fluid. That comes into the turbine. Okay, and so another way to characterize this is that's pretty much it. So it's basically, and again, this is less than 1. The turbine is going to be less than 100% efficient. Typically, ideally, it would be 100% efficient. So the fluid that comes into the turbine is going to have more energy than what you recoup through the shaft. Just a second, let me go ahead and create a new page here, and it may help to just draw what I'm talking about here. If you're not familiar with a turbine, but basically the symbol that we have for the turbine, let's say T, is this trapezoid, and what we have here is we have a shaft that comes out like this, and then we have a fluid input, and an output, or an exhaust. And so typically what you have here is you have fluid coming in, typically steam, and then fluid coming out. And so the energy, there would be an energy rate associated with the fluid that's coming in, and there's an energy associated with the fluid that's coming out. And this, I just reversed the order of the fluid. And what you're producing is you're actually having, and ideally you would want work coming out of the shaft here. So what we're doing is we're changing the energy. We have high energy fluid coming in. We're grabbing some of that energy and converting it to shaft work. So the change of energy of the mechanical fluid. Let me go back to the regular colors that we were talking about. So if we said the change of energy of the fluid is equal to the energy of the fluid as it comes out minus the energy of the fluid as it enters. Okay, because I reversed the fluid and this is out, but this is basically the same as this. All right, I just kind of reversed the footer there, but it's the same one. And this one is this E of the fluid in is basically this here. Okay, so that's how we measure the efficiency of a turbine. Again, if you just, so for being consistent here, we'll see the efficiency of the turbine is equal to what's coming out. It's basically the work of the shaft, and what's going in. It's basically I can't say it's just the energy coming in here is what's coming in. Yes, it is, but the total energy that's being recouped by the shaft is the difference between the energy in and the energy out. It's not just the energy in by itself, because energy out, there's some energy associated with it's not this energy out is not zero, because the fluid has to flow out and go through the rest of the system of the turbocharger generator system, right? So there's still energy content there. So it's basically the difference that we put at the bottom here. And again, that's, we'll just say mech fluid. And that's basically the same as this. It's the same. I just put, it's the same thing. All right, and there's other, go ahead and talk about the other type of efficiencies. And I have to start a new page here. Sorry, learning how to do this. All right, so if we're talking about a motor, just a generic motor, but typically we're talking electric motor. So an electric motor, I'm going to draw it up here, is going to look like, here's kind of what an electric motor is. We have a shaft that goes like that. We have the motor mounts, where it's mounted onto a surface. So I'll just put M here for motor. And then we have, it's electric motor, and we have a plug that goes into the wall. And so what's happening is we're getting electricity. If we draw a control, I guess we don't have to include the ground. We draw a boundary. Then if I'm going to go ahead and just use different colors we have, this is what we call work shaft out. It's typically it's a rate. And for another, we'll use a different color for work coming in from for the power here. We'll call that work electric in. So then we have that the efficiency of this motor is equal to what's coming out. What's work shaft out is coming out. And what's coming in, well, we got work electric is coming in. And the electricity that comes in to power the motor is going to have a larger energy content than what comes out with the shaft work is, because we have inefficiencies, right? We have heat. The number one inefficiency is friction that produces heat, and so there's actually going to be heat escapage. And this is very important here to understand, but all motors are going to produce heat. And then the most efficient motors produce the least amount of heat. And 100% ideal motor would produce no heat, would be 100%. So the energy that is lost in the system is in the form of heat, primarily due to friction, but it could also be sound, vibrational, as the motors are shaking, and there's kind of energy being transferred to the base. There's sound. If you can hear it at all, then there's energy associated with the sound. It may be small, but it's enough to basically vibrate your eardrums, so there's some energy there. But primarily it's heat is the biggest energy that causes the inefficiency. All right, and then another, we'll go and talk about another efficiency. So a generator. So what's a generator? I'll draw a generator here. Basically, a generator is a motor in reverse. Let me go ahead and draw that. It's the same motor. And instead of getting shaft work out, we put work in. So we get, because we want to produce electricity. Alright, and what we get, instead of, for the motor case, we get an input of electricity. What we're going to get out is electricity. Sorry if you hear my dog, I'm so sorry. He's freaks out whenever he doesn't understand what's going on. I'm outside and he's, sometimes I can't stand that guy, but anyway, sorry. Alright, so in the generator we're getting, it's the reverse of therefore we should have a reverse, we should have this swapped here, right? And that's what we swap the terms for the generator, and we say that the efficiency of the generator is our output, which is the electric, I'm so sorry, electric out over work shaft in. And then we can actually have different, we can do combinations. We can actually have efficiency of a pump that's attached to a motor, right? And that makes plenty of sense. So this is pump. Sorry if it's, I'm not that good with this drawing tool here. So this is pump and a motor combination. So that would be, for example, I don't know, let me draw a pump here. Typically a symbol for a pump looks something like this, where this is P, and then there's fluid that comes in and fluid that comes out. So there's actually a shaft we have to be able, in order to power the pump, we rely on a motor, typically. And that's the motor that I just drew up there in green. I'll just put an M here. And that is powered by an electric cord, typically. And so this combination here, the efficiency of this combo of these two components is equal to the efficiency of the pump. I'm just going to put NP, or A to P, times the efficiency of the motor. And you could also look at it in terms of what comes out and what comes in. It's kind of hard to draw the control volume here, but I'm going to go ahead. I'm going to include the pump, but I don't want to include the input of the fluid. I want to be able to have the fluid cross the boundary, so I'm going to do something like this. So there's work coming in from the electric plug. There's energy coming out of the pump, and there's energy coming into the pump, like that, from the fluid. And so the efficiency, we can also say, is basically the change of energy of the fluid that we talked previously divided by what's coming in is the electricity, right? So I'll go ahead and just change that to yellow and say it's basically the electric work that's coming in. But if you already know the efficiency of the pump and you know the efficiency of the motor, it's much easier just to multiply the two and get the total efficiency. So if, for example, if the efficiency of the pump was 90% and the efficiency of the motor was 90%, then when you multiply 0.9 times 0.9, you're going to get 0.81 efficiency. So as you start connecting components, you actually get drops in efficiency.